Okay, guys, I will be trying my hand at making one of these study videos for you guys. If it's awful, I'm open to critiques, so let me know what I need to do. So we're going over Chapter 6 materials because that's one of the main things that we weren't able to talk about in the library. So really, Chapter 6 is all about organic reactions. And that's kind of what I was telling you guys, that it's going to start picking up and you guys are going to be focusing more on the actual reactions of chemistry and not just getting the basics. But the basics are really important in understanding how these reactions occur. So the 4 main types of reactions, and if you hear me yelling, it's because my cat is bothering me. And we've got 4 main types of reactions. I don't know if there's more. Like category-wise, we just kind of expand upon it. So there might only be 4, but whatever he tells you. If there's only 4, or there's 4 main ones that we're going over. Reactions. I'm going to shorthand. So we've got substitution reactions, which are probably like the most straightforward. And it's just swapping. So you've got AB plus CD yields AD plus CB. And you can kind of see, we just FOIL method it. And so the reason it's AD and CB and not, let's say, AC plus BD is because typically when we see this primary one, or like the first letter we see, is going to be our, too thick, is going to be our like cation. And this is going to be the anion. This will be a cation. This will be the anion, which you can't have 2 cations, right? And 2 anions. Those won't bond. So that's the reason it's specifically ADCB. So next we have, now it's too thin. I'm getting my life together. Obi, get down. Okay, then we have addition reactions. And I'm going to absolutely cry if this isn't recording the audio well. I'm so sorry. Addition reactions break double bonds. So that's the easiest way to think about it. They break double bonds. So let's say we have A double bonded to B, and then we throw C into the reaction mixture. And it's going to break the double bond and form A still to B, because it just broke the double bond, and then each of these will be bonded to a C. Okay, and then elimination reactions is the exact opposite. It's going to be forming a double bond. Okay, so we've got, if we had still this very same one, AB, both of them bonded to a C, right? It's going to cut its connection to C, and it's going to throw the electrons that it has left over because it lost its bond to C into another bond with each other. So then you'll have leftover C. And then the last type of reaction will be rearrangement. Or aka isomerization. So we know that isomers is just the same like formula, but it's built different. So that's exactly what this is. We're just changing the way that the structure is built. We're not adding anything to it. We're not taking anything from it. We're just changing the way it's built. So if we have a CH3 bonded to a carbon, bonded to a CH3, another methyl, bonded to a CH, and then this is doubly bonded to a CH2, right? And then we're going to turn it into, it's going to be built a little bit different. We've got methyl, 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 methyl. Okay, so looking at this, we've got the same number of carbons. So we've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 carbons. We've got 3, 6, 9, 10, 11, 12 hydrogens. 3, 6, 9, 12 hydrogens. So we're exactly the same. We started as C, I already forgot. 1, 2, 3, 4, 5, 6. C6, H12, and we ended as C6H12. We just changed the way the structure was. So the best thing to do with rearrangement, like if he asks you what kind of reaction it is, make sure you count all the atoms. If you have the same number of atoms, then nothing changed, right? We didn't add hydrogen, we didn't add carbon, we just changed the way that it looks. Okay, so those are all your reactions. I guess the next thing to move to would be probably calculating delta H, which is just bond dissociation value. That has to do with reactions, so it's probably going to be the next easy thing to move into. So we've got, bond dissociation. And I'm thinking about this. I'm not exactly sure how I'm going to send this video out to you guys, but I'll figure it out. Obi, get down. Okay. AKA calculating delta H. Oh. Hello? Okay, so the formula is bonds broken minus bonds formed. Right? So, AKA reactants minus products. You know, normally when we find delta anything, it's products minus reactants. Not in this. It's reactants minus products. So what you'll have to do is determine exactly what bonds are broken and then what bonds are being formed. And then you guys are given a chart that tells you like the energy level of it. So we're actually going to go through a practice problem. I screenshotted this. Oh my gosh, so cool. So we've got this. And then I screenshotted the chart that you guys will be given. This will be given on the test, so don't even worry about trying to memorize anything, right? Okay, so I would recommend drawing your reaction out. So we've got two methyls bonded to each other, right? So essentially we're looking at CH3 bonded to a CH3. And then we're adding an F2, which is just an F bonded to an F, right? And we are forming two CH3 F bonds, right? So technically we've got another one here. This is what we made. So bonds broken. So our methyls aren't bonded together anymore, right? So this was broken. And our fluorines aren't bonded together anymore, as we can see based on the products. So this was broken. This is going to be the only math you'll have to do, and it's unfortunate because you don't get a calculator, so I would just write out the math. Okay, so, and then we're forming, let me use a different color. We're forming these, right? We're forming two of them. Ooh, rotate that. It's not going to let me. Mofo. Okay. So now we're going to look, right? We're going to identify where is a methyl-methyl bond on this chart. So it's a carbon bond, right? Which we know is represented by R. Any like R group is like a carbon type substituent. So if it's a carbon, like a methyl bonded to a methyl, it's going to be an RR bond. Do you think? Okay, so we've got this one right here. Right, there's our methyl-methyl. And then Z bond, we've got fluorine-fluorine. We've got that there. And so we are working in delta H, right? Kilojoules per mole. That's very important. Do not calculate from this end of the chart. We're working in kilojoules per mole, not kilocalories. Okay. So now that we found that, we're going to look for what our product is, which is CH3F. Perfect. Now we found everything. Okay. And again, it's reactants minus products. Oh, it's not going to fit. Okay, so we have our original methyl-methyl. This is 368 kilojoules per mole. Plus, our fluorine-fluorine bond is 159 kilojoules per mole. Okay. Minus our reactants, or product, we've got 2 moles of it, so 2 times our methyl to fluorine is 456 kilojoules per mole. OB. Fucker. Pardon my French. Okay, so like I said, you're not going to get a calculator on the test, so go ahead and just write it out. No need to be embarrassed. I did it. I was not going to get this wrong just because I didn't do the math right. So 2 times 6, that's 12. We carry the 1. 2 times 5 is 10, plus 1. We've got 11, carry the 1. 2 times 4 is 8, plus 1. We've got 9. Okay, so this is our products, and this is in kilojoules per mole. Okay, so now down here I'm going to do 368 plus 159. 9 plus 8 is 17, so carry the 1. 6 plus 5 is 11, plus 1, that's 12, carry the 1. 3 plus 1 is 4, plus the other one, 4. Okay, so now we've got 427 minus 912. Okay, so now this is how I do it. If I know that this number is significantly smaller than this one, right? Then I know it's going to be a negative number. So I know that my answer is going to be negative, but you can still just subtract 912 minus 427, because that's the way we do math, right? So then we borrow this one, that's 12, minus 7 is 5. Borrow 1, we got 8. 11 minus 2 is 9. 495. Did I do this right? Let me see where I messed up, guys. $456, $159. My math isn't mathing. Let me see where I messed up. You guys need to do better on your exam. Let me get a calculator, though. OB. Anyways, yeah, guys, if you didn't catch it, that's a 5. There's where my math is wrong. Okay, 5. And then hold on. So we've got 12 minus 5. Oh, duh, because that was a 0. That got turned into a 0 when we borrowed 1 from it. So that's 10. Minus 2 is 8. And then 8 minus 5 is 3. There we go, guys. See, this is common mistakes. Don't mess up on your math. Okay, so we've got 385, right? But we knew it was negative because our products ended up with way more. So we've got a negative 385 kilojoules per mole. Answer is D. And I was correct. Okay, so don't mess up on your math. Double check it. You don't get a calculator, so it's unfortunate. Don't let simple addition and subtraction mess you up, especially if you understand the concept. So hopefully that made sense. The only error in it was my math. Sorry, guys. There you go. So that's bond disassociation. It's not that hard, and I don't think he has that many questions on the exam with it. There was only like maybe 1, maybe 2. Okay. So now that we've got that, we can move into breaking covalent bonds because I feel like that flows nicely with where we're at right now. So let's do that. We've got breaking covalent bonds. And honestly, I highly recommend you guys go based off the learning objectives that he posts for each chapter. And if you can understand those, really that was key for me. That's what I did studying for the final, is I went over all the learning objectives. And if you can do those, you should be fine on every exam. So you've got 2 types of covalent bond breakage. Oh, also I thought we should probably talk about the fact that it was negative. So remember when we would talk about endo-exothermic? Yeah. So endo-exothermic, it was negative. So that means we released a lot of heat. So this type of reaction is exothermic because we ended up negative. Anyways, just thought that tie that back into your Gen Chem. So we've got 2 types. We've got heterolysis. Is when everything goes to one side. So we've got A bonded to B, right? When this bond breaks, all electrons will go to B. Plus B. So that makes B negative, right? It took on all of the electrons, and A is positive. So this is the typical, like if you had NaCl, right? That's like the typical bond breakage of it. Cl takes all the electrons because sodium is happy to give it to them. So we've got sodium and chlorine, right? So that's the typical bond breakage that you see. Sorry guys, my cat's being a menace. Okay, that's the normal one. There is also homolysis when they share. Which is radical chemistry. You guys don't do that here, but in OChem 2, we'll do more like radical, there's like radical bromination, things like that. So it's a half arrow because they each take only 1 electron. And these are called radicals. Oh my gosh, I gotta light a candle. My cat just shit and it stinks so bad. Okay, sorry about that. So that forms radicals. Okay, so those are the two types of bond breakages, and they are both of them are endothermic reactions, right? Because you have to put energy into the pot to get them to break their bonds. So it takes energy to make a bond break, which we saw that right over here, right? So our reactant side was positive, and then our product side was negative. Because you have to put in energy to get bonds to break, and then they release energy as they form. Okay, so I hope that makes sense. That's really all there is to it. I would just watch out, because sometimes when he gives you like reaction mechanisms or things like that, he'll use a half arrow, but 90% of the time it should be a full arrow, because all electrons move together. Only in radical chemistry do you see it split separately. But he'll have like a specific homolysis question. I think I remember having one like that. Okay, so that's that. Let's move. Just a quick definition. I'll come back here if I think of other definitions. Like definition questions, because he has some of those. Y'all know that. Catalysts. They increase the rate of reactions, which we know that from biology. We know that from almost everything we've ever done. Catalysts increase the rate of reactions. Which leads me into our next thing. We have reaction coordinate diagrams. Okay, so let me draw one for us. So we've got something like this, right? And then this side is a measurement of energy. Measures energy. And then this side is literally just the reaction coordinate. It's just labeled RC, reaction coordinate. Which just means, like, where are we at in the process of the reaction? Where are we in the reaction? Okay. Let's just draw it simple. We'll do one curve. So we've got okay. So I will be labeling a whole bunch, but the top of this hill down to the bottom of like where we started. Oh, hold on, I forgot we can change to, I think it's this button. There we go. Yeah. Okay. This is the activation. Oh, I forgot to take that off. The activation energy, which is just how much energy needs to be in there for the reaction to occur, right? The top of the hump will be labeled like this, and it's the transition state. The transition state, which is just like when the molecule is like in the midst of changing, that's the transition state. When it's like kind of halfway through the reaction and it's like changing, it's not quite where it was when it started, but it's also not what it looks like when it's going to be done. Okay, so that's the basics, and then we've got SM, which is the starting materials, basically just our reactants, what it looks like when we started. And then over here, we've got our products. P, it's our product. And then we've got, let me see, that's a good color. I think that's different enough. Okay, between these two purple lines, which I didn't make a big enough difference, clearly. But between these two purple lines is our delta H, which is the overall heat of our reaction. So kind of like when we were doing our math over here, right? We've got reactants minus products, and then we got the results of this. Oh, it's so thin. Solid. That was this, right? That's our delta H, which is the overall heat of the reaction. That is represented by this tiny little gap between the end of the bottom of the products and the bottom of the starting materials. I didn't make mine very big. Most of the time it's a more obvious difference. So this would be a one-step reaction, right? Why? Because there's one transition state, like we got over one hump and then we ended up our products. So that's a one-step reaction. If we were to do a two-step, we'd have, so we've got this and that, and I'll make it a little bit more obvious. Okay, so again, we've got our transition states, but now we have multiple, right? It's a multi-step reaction because it changes twice. So we've got a multi-step reaction, and we've got, what did I mark it over here with red? Activation energy. This new little guy down here is the intermediate. It's the intermediate structure. So it's kind of like we're in limbo here. We're not fully done with our reaction because we've got another step, but we're relatively stable in this little ditch we've got. So we're not too worried. Product, and then what can I mark starting materials with? Green. Starting materials. So I made it a bigger difference. So again, we've got, and then that is our delta H, overall heat of the reaction. This is a two-step because we've got two transition states, so it's like, oh, we've changed twice. Changed twice now. Let's see. I think so like in a reaction. Oh, I should do one. So you'll have one where it's like, why did we talk about the catalyst, right? So you can see a catalyst on a reaction coordinate diagram. So normally, it looks like this, right? Also, if your product is above the starting materials, that means you were endothermic. If products is higher than starting materials, then you are endothermic because you absorbed heat, right? Like you have more energy now because you had to absorb heat. If your starting materials are above your products, then you are exothermic because that means you released heat. If your products are at a higher energy level, right? Because it's energy. So our products are at higher energy level than a starting material, which means it had to have absorbed heat. Versus, I didn't draw an example of it, but if it was like that means your products are at a lower point than your starting materials. That means you expelled heat or energy, right? Okay. He might ask a question about that, so just a little detail. But, so here, this is a normal reaction coordinate diagram, right? But he'll have these little dots, and this dotted line is a catalyzed reaction, because if we look here, it has a lower activation rate, right? Why? Because catalysis speed up the rate of reaction, so it doesn't require as much energy to activate. So it gets over this hump and it'll be much faster than if it wasn't catalyzed. So the dotted line is with a catalyst. Okay. Yeah. So that's what we've got there. I think we should talk about rate laws, moving on from there. So we've got rate laws, which is just a written form of the reaction coordinate diagram, essentially. So I know we did rate laws in Gen Chem. I don't know if you remember them. It's fine if you don't. So rate is equal to K, and K is just a constant of the reactants, right? But we were talking about like the steps of a reaction, right? So if it takes one step, which is what we were looking at with this one, right? A one-step reaction. Let me do a different color. One-step reaction. This is a two-step reaction. Okay, so with a one-step, it is a second-order rate law. So it's going to be inversed, right? Second-order rate law. Why? Because in a one-step reaction, like, do I have an example of these? Yes. So if we have A bonded to B, and then we're adding C into the mixture, right? This is got the... Okay. We're going to end up with A plus B bonded to C. Why? So we have these electrons are stealing B, and then all the electrons are going to A, right? This is just an example reaction. Very simple. So these electrons want this B, so they take it from A, and A is left with all the remaining electrons from the bond. But all of this happens simultaneously. And you're wondering how, because it's written like this, right? If it wasn't simultaneous, there would be an extra step, but there's only one reaction arrow, which is a sign of one step. One reaction arrow equals one step. Okay, so it's a second order rate law because it all happens simultaneously, which means the concentration of every molecule here in the reactants matters. So then we've got the rate of this is equal to AB times C, right? All the reactants matter because it happens simultaneously, so all of them could be a limiting factor. And because you've got two, right, because technically these are all, they've got the one in here, which makes it second order. Okay. For a little two-step reaction. It is first order. Okay, so I'll give you guys an example of, get down, Obi. Give you an example of a two-step reaction. So we've got A bonded to B, right? The first step is going to be this bond breaking. So then we've got A already plus B, right? And then we're throwing a little bit of C into the mixture here. And I realized that I've completely changed the signs of these. Like, in the beginning when we were talking, I made the point of it being like anion, cation, blah, blah, blah. But this still stands. Because, everything, like if we did NaCl plus, I don't even know. But normally, the cation here is listed first. And I get that I changed it, but it's just for the example. I hope that doesn't confuse you guys. It's a little unimportant. It's just a bland example. Okay, so first the bond breaks, and then we add C in, and then these electrons are going to grab B. And then we've got A electrons plus CB. And everybody's happy. But I guess I'll draw it with a bond so you guys can see it. C bonded to B. Okay, so this is a two-step. Why? We see two reaction arrows, right? But the only step that really mattered was this one because it's the first step. So this is the limiting factor in the entire thing, or AKA rate determining step. Because depending on how much of this you make will lead to how much of this you can create. Because however much AB splits, that's how much B is left over. And that's all that can bond to C. So it's the rate determining step. So its rate will be just AB. And there's only one, so that's why it's first order. Sorry, my phone's blowing up. Okay. Yeah. So I don't know what else really to talk about for chapter 6.